Welcome back to all of you for the online computer vision classes. As I said, these are the sources, particularly Professor Aaron Bobbick's lectures are the main source of these slides presented and the discussion as well. And we discussed about in the last class, we have seen what is it means by motion estimation, different applications of motion estimation, and why motion estimation is important. And then we have seen what is an optical flow and an example of optical flow here, which gives us a dense motion estimation in a way. But again, we have also noticed and discussed in detail about the fact that this is gives you an apparent estimation and not necessarily it estimates the motion at every pixel properly there, particularly when there are uniform regions. Then we started formulating this optical flow problem with the example that you have two frames at a time frame at a frame t and subsequent frame t plus 1. Essentially, optical flow problem is about in its neighborhood finding out where this pixel has moved, and this is based on the intensity values, and that's why this is also the constraint imposed in optical flow is referred to as brightness constancy constraint. And then we started formulating this where, for example, if you are looking where this pixel at location xy has moved to in the subsequent frame, what you are going to do is you are looking at where the same intensity is present in its neighboring region. So we are assuming that there is a movement of u in the x direction, v in the y direction. So this equation now turns out that you are trying to find out u and v such that the intensity at x, y location in the teeth frame is equivalent to the intensity at x plus u, y plus v location at in the t plus 1th frame, right? Then this is where I left you in the last class, asking you to figure out how to derive this equation and also try to plot this for, let's say, the varying values of u and v and see if the solution is unique or not, and get first some interpretation on the possible solutions to this equation based on the equation itself, and also then by geometrically plotting this equation of that particularly that inner product and see what would happen. What is the equation that we got? I of x comma y in the teeth frame is equivalent to you want to find out u comma v. These are the parameters or unknowns that you want to compute in the t plus 1th frame where these intensities are matching. So this I can write the same thing as bring it to one side, y plus v comma t plus 1 minus I of x comma y comma t. So we are making an assumption already said that this is for very small movement within that displacements are there from one frame from the teeth frame to t plus 1th frame. So Taylor series expansion can come to your rescue to write this around I of x y comma t here. Okay, given that u and v are small and you have good, these frames are not too far away there. So how do you write this in terms of that? How do you expand it? Just keeping the first order terms, I of x comma y comma t plus x y t comma
D
dou
dot
dou dou x.
X
Okay, dou x. What should I write here then? Multiplied with
U
u. Very good. And then what's the next term? Dou I of x comma y comma t
by
by dou
dot
y times
V
v. Very good. And then what is the next term here? Dou I of x comma y comma t by
dot t
dot t times.
times 1 size v.
Right, that's something as a little bit you have to pay more attention there, because here if you notice you are expanding it over x y. So here what you are doing, x plus u minus x, that was giving you u here. Similarly, y plus v minus y is giving you v here. On the other hand, here you have t plus 1 minus t, that should give you here 1. Hope that is clear to everyone. Please let me know if you have any questions here. Minus of I of x comma y comma t equal to 0. So that's the approximate expression where I am ignoring the higher order terms. So now you could see these two are the same. Okay, now let me drop anyway. Everything is these values are x y comma t. So let me write, for example, in slightly polished notation to make it crisp. Is, let me write, if it is by dou x, let me write it as I subscript x, okay, for my convenience. Similarly, if it is with respect to t, I subscript t. So in that way, if I use that notation here, so that's equivalent to ix times u. So essentially ix is derivative of the intensity value of the pixel which is there at x comma y location with respect to x. Hope that is clear to you. Then plus iy times v. Okay, these are with respect to x and y. So then this on the other side, if I take this term, that's equivalent to minus it. Okay, this is the referred to as brightness. This is what you would like to do here. Okay, it's moving somehow. Okay, any questions so far? This is a very important equation in optical flow, as I said, referred to as brightness constancy constraint, right? And any questions so far before I do further analysis of this equation? Let me slightly now rephrase this equation. Okay, before that, see, unknowns are two here. Unknowns to be computed are, there are two unknowns here, those being u comma v. I'm sure everybody is clear with that. If not, let me know. And then there is just one equation. So if you just look at in terms of the equations, suppose if you are given two frames, okay, I of x comma y comma a teeth frame and another same image but with the next frame of t plus 1. Obviously, you could compute at a given pixel ix, which is nothing but the derivative in the x direction you can compute. Iy you can compute. It you can compute, right? Because that's just for that pixel here. Okay, in that time you take the derivative, and with that, you know, it. Now, two things are remaining. So from the equation, you could say that if you can take, since you need to satisfy just one equation, if you are imposing just this one at a pixel level, not worrying about its neighbors, displacements, for any given you could come up with a v. So it's not a single solution, but would rather a set of solutions is what you have here. Hope this is clear. If not, let me know. And let us make a slight rewriting of it to get more insights into it. So let's go into the vector notations. For example, we have seen this enough number of times by this time. Ix and Iy is nothing but the gradient, right? And then I could write it as u times v. Okay, 1 cross 2, 2 cross 1. That would give me minus it. I could write it in this manner. Okay, so this is nothing but if I treat them as vectors, let me write this as gradient of I. Okay, you are having a vector of one by, it's a horizontal vector, a row vector, for example. If you consider uv also as a row vector, for example, this is your vector of u comma v. If you are considering, that is equivalent to taking a dot product of this with this, right? That would give you minus it. Why am I so interested in, or what is that gain that I would be getting by writing it in this manner? Well, let's try to get an interpretation now in terms of, okay, very strong edge is there. I'm interested at this point. What is this one? This is the gradient. Say, for example, if I have an edge like this, obviously my gradient is something like this. Let's consider as my gradient of I. Okay. I'm sure now everybody is comfortable with gradient. We have spent enough time on that. Now, this dot product of this with u comma v. So dot product, in another words, if I have a vector, let's say a bar, okay, and let's say I have a b bar vector here, what is the dot product equivalent to in terms of projections? What can you say about dot product? Is essentially this angle is theta. So this is b cos theta. You are projecting that here, right? So that multiplication essentially would give you the value there. Similarly here, now this is your gradient I, and you need to find out the values of u and v. So let me draw something here, a line. Assume, despite my wonderful drawing, jerky drawing, that that's a straight line which is parallel to this edge. We assume that. And now this, well, you also consider this is giving you somehow the values of u and v, that vectors, these are all the vectors of u and v. You assume now, assume that this is my gradient of I, okay, and consider that equivalent to minus it here. So instead of this, assume that this is the value you got, minus it. This being a dot product there, that essentially would be a projection onto this line here, right? This being minus it, that comes to on this line, and from this point to anywhere on these lines would all result in same value of projection. Is that clear? Because once you are taking projection here and multiplying with gradient of I, all of them would give you the same result. Hope this is clear to you in the first place, where I am telling you there is an edge here. This is giving you gradient of I direction. Then I need to find out the u and v that would result in minus it. Okay. And assume that this value is minus it in this direction I am plotting. And you could see all these would give you the same value of minus it. And these vectors are representing the some sets of u and v values, which would have same projection values. Okay. So far, I think it is clear to you. Now, you rephrase this and interpret it in slightly different way, where I want you to interpret this in terms of a component which is parallel to the gradient, a component which is perpendicular to the, stop me if something is not clear. See here, we have arrived at this equation, gradient of I, its inner product with u and v is going to give you minus it. I know gradient of I know it. Okay. So this is a vector. It's this vector's inner product with another vector is giving me a scalar. That inner product, the resultant is minus it. That's what I'm getting there. Now I'm coming here. I know gradient of I know it value. So that's the inner product. So all you could see here, if this is an it value is this much here, for example, when I take projections for all these vectors that I have plotted would result in the same solution. Now, my question is, what is unique here? Unique solution is there. Earlier, I interpreted the solution in terms of u and v. Now, I want to make an interpretation of the solution in terms of components. The uev is essentially a vector, is it not? When we take projections of that vector perpendicular for along the gradient delta I, parallel to the gradient and perpendicular to the gradient. Suppose I have something like this. Okay, assume that this is my, I am just reorienting that my gradient is like this. I could always make, yeah, even this could be even small. I don't mind because I'm more interested in the direction here. Then I could always write this as this is my vector u and v. I could make a projection of that across the gradient. Okay, let me call, I don't know what to call it, something which is parallel to some ua and ub. I could do that. Okay, u bar, if I call it as a vector there. Now I would like to ask you, what is unique here is that the component which is parallel to the gradient are perpendicular to the gradient. I hope at least
The
I'm
parallel component.
very good. Now you interpret in terms of the edge now. Posing this brightness constancy constraint, suppose there is an edge. What is the component that you could exactly compute? What is the component that you are not, there is not a single solution that you could come up with?
Component which is perpendicular to the edge can be uniquely determined, and
Correct.
along the edge cannot be.
Very good. Very good. And this is known as,
I think we called it aperture problem.
that's right. Very good. Again, we are looking at the aperture problem here. Look at here. This is your initial one. Now, this hedge has moved in this direction as well. So this has come to from here, it has come here. Okay, this is a movement perpendicular there, and this has moved there. And when you are looking locally, if you see something like this, okay, there is all you could say is perpendicular to the edge. How much you moved, you could say, but parallel to the edge, how much it moved, you cannot say. And when you are looking just locally, see another example here. Suppose in the first image you have something like this, second image there is something like this. Okay, all you could say here is this image has moved in this direction. Okay, in this direction this image has moved, but the original scenario could be this movement, but along the edge how much it has moved you cannot say, for the simple reason that while this object is bigger here, this might got mapped to the this way also it has moved, and then it can map to any other point there, which there is no a single solution, right? So when things move like this, all you could say is perpendicular to the edge how much it has moved you can say, but you cannot say how much parallel to the edge along the edge. Suppose if the object has simply slided down, okay, this I have an object here, this object has I have a bigger object, this has simply slided down a bit, and if you see in the small aperture, you could never realize that the object has moved unless you are taking again another this has everything has moved this way if you are considering it, but you cannot uniquely say, there are different possible solutions. So it is only the component which is perpendicular to the edge you could say for sure, if you are imposing just the brightness constancy constraint. Now thanks to the inner product formulation of this, from this now we got the clarity in interpreting this equation in terms of parallel to edge, perpendicular to edge, the components of the displacement. Is that clear? Take a look at this equation. Suppose I take multiple pixels, I compute this ix, iy and all for all the neighboring pixels. And then if I impose a constraint that for a given pixel, the whole patch is expected to move with the same displacement. It's like you have an image where the car is moving. Now you are assuming that all pixels, if I take any one, assume that I ended up in picking up one pixel within the car from one frame to the other frame, you expect that whole patch would have same displacement. So you write this equation for whole pixels that are there in a small patch around your pixel of interest, and then you solve, and then you solve those set of equations to compute u and v. So before I do that part, let me first summarize here the same thing, but in a more specific terms we are going to mention here. is the fact that optical flow is not necessarily a motion flow, because there is an aperture problem as we have seen it. We are now talking in more definitive terms here. Because of the aperture problem, you could never for sure uniquely know the motion of the object parallel to the edge that is there in that image, although you could compute uniquely its component perpendicular to the edge, right? So near an edge, we observe the component of flow perpendicular to the edge is something we could observe, but cannot measure the component of flow parallel to edge. And of course, this is not the only reason why optical flow is not equivalent to motion flow. Another point is we have seen it in the earlier images here. Let's say that dice thing here, although there is here, forget this, since whenever there is no edge, there is no way even you could compute here. If at all there is, you look at that region is essentially corresponds to this region. The question is there a motion in this region or not? The answer is yes, because you could think the whole base is moving on. But because that's a uniform region, there is no way you could figure out, unless you want to definitely make u and v, you want to make a move from there. Okay, still you will find some uniform region, so you could make a move. But despite making multiple moves, you could have multiple, still you could get the same solution for that equation. So if you are making a move only when there is an intensity difference, and then if you are in a uniform region, you would remain there same. So while there is a motion in that uniform region, that cannot be detected from the optical flow. So whatever we formulated, this is what we are now referring to. This is what we are referring to as optical flow. So through that, it gives you a zero displacement. So in those regions also, optical flow and actual motion are different. So that's why we are writing here as optical flow is not equivalent to motion flow, because you cannot observe anything in the areas of constant intensity. So you could see there. Now let's try to interpret the very equation itself there without even worrying about the dot product way of writing it. You simply had an equation of ix times u plus iy times v equal to minus it. And this u and v are two variables are there. You know ix, you know iy, you know it. So one equation, two variables, no multiple solutions are there. Basic idea is impose additional constraints there. That's all, as simple as that. So if you want to, before doing that, for the sake of convenience later, let me call the brightness constancy constraint as e subscript c. So hope you are also making the required notes. The what is it that's it's going to do is, you are going to minimize for all pixels ix times u plus iy times v plus it. Okay, well this cannot, if this cannot be zero, you would, well you would you might make, essentially you are minimizing it. Well, not really so, because this can have negative values, so I could write this as this minimization square. Obviously this is zero, when this is zero, that is minimum, right? And I will take the square to get rid of the zeros. And this is how I could so then how could I write it? Maybe I'll slightly write that in a different form here. Let's say uh, here, so this is basically, let me call it as ec cap is something that mean compute values of u and v such that this minimizes this. And of course this at every pixel you have to, you'll be considering. Are you okay with this equation that I have written? I'm trying to write it as a minimization problem, because as you could already sense, I'm trying to add some constraints and then minimize that further. If not, I end up in 0, but I would like to get minimal, just like we did with least squares and other areas. So are you okay with this equation where I'm simply, you, this is a x into u plus iy into v plus it equal to 0. If not, make it 0, you bring it to 0. So that's exactly square of it. I take it every pixel, I compute ix, iy, and so on. Okay, hope that's clear. Now the smoothness constraint I am going to impose is, as a first step, you let me put let me consider the entire image. Let us consider the entire image here as a first step. And then how can I write, let's say smoothness constraint, let me call it as e smoothness, is equal to, what I would do now is, again for all pixels in the image, u subscript x square plus u subscript y square, okay, plus v subscript x square plus v subscript y square. This is what I want to minimize or put as smoothness constraint. Can anyone attempt at giving an interpretation to what exactly this equation is doing? For example, I consider one pixel here. So how do you write this? For example, let me call u of xy is essentially the motion at this pixel. See how many vectors, how many values would, how many displacements will be there at a given pixel? Is it a vector or a single displacement we are writing?
U and V, sir.
Right, v of xy is there. Now, for this, assume that this is my x direction for the time being. Okay, this is my y direction for the time being. Then what is the values of u and v here? What are the indices for u and v here? X plus 1 comma y, and v of x plus 1 comma y. Now let me also write just for this, that's where I will stop. So this is equal to u of,
X
X
comma
comma
y
Y
plus
plus 1.
one.
right, and v of same, of course the index would be same, because that's essentially the pixel index. That's all I am writing. Now you tell me ux for a pixel which is at a location x comma y, okay, using forward difference scheme, you tell me that value. This is equal to,
U of x plus 1 comma y minus u of xy.
good. Similarly, if it is u, u x is there for me, u y is there,
Y.
that also let me write it now. For u y, you tell me now what should be the value.
U
U
of
of,
x comma y plus 1 minus
mhm,
xy.
minus u of x comma y. Similarly, let's come for the sake of completion, you tell me vx of x comma y equal to v of,
X plus 1 comma y
hmm,
minus
minus,
u of xy.
right, and vy of x comma y is now derivative of this displacement in the y direction using forward scheme. So I would write x of y plus 1 minus v of x comma y. Good. Now you tell me what each term is. You simply consider you are minimizing each term independently. That's just a linear combination of squares of those terms. So what is it equivalent to saying that square of this should be minimum? What does that would tell you? What is the interpretation of that? I want the square of this value to be minimum. What does that mean in terms of this image? You tell me now. So let's call this as a horizontal displacement. Okay, u as a horizontal displacement, v as a vertical displacement. Now you tell me what it means by minimizing ux square term.
The U values essentially should be the same if all
That's
of
right.
these
That's
values
right.
are low.
So in slightly rephrasing your statement, this is ensuring that A pixel which is next to it in the horizontal direction has the same displacement as this one, and this is ensuring that a pixel which is above it has the same horizontal displacement. This set is looking at the about the vertical component. Now this is ensuring, because it is looking at x plus 1 and x, a pixel next to it in the horizontal direction has the same vertical component. And this is ensuring that since it is looking at y plus 1 and y, a pixel above it has the same vertical component. If I just shuffle them a bit, it is making sure that this pixel and this pixel, if I look at x plus 1 y, then I could combine, for example, if you want these two, first I look at these two, are ensuring that a pixel next to the right side of it has the same u and v values as this pixel. And if I combine these two, I could interpret that a pixel above it has the same u and v values. So they are moving with the same displacement in the x and same displacement in the y. But in one case you are looking a pixel which is in the same row, and in another case you are looking at a pixel which is in the same column, and you are doing this thing for all the pixels. Is this clear? Because if I give you, you should be able to calculate it and give those things to me. Is this clear, or any questions on this?
So like if there are two images,
Hmm.
so we can calculate u and v values for each pixel, right?
Right, correct.
So then if for neighboring pixels, if they have same u and v values, that means they're
Hmm.
moving together with respect
That's right.
to
That's right.
the first image to another.
Correct, correct. That's,
Okay.
you are right. You are right. If I am going to impose this constraint alone, what it does is it enforces that all pixels have same u and v values, because then only, because this would this is when I do it at this pixel. Now my xy location has changed to this, then it will impose that these two pixels have same u and v, and these two pixels have same u and v. Now from here I move to this, as I am doing for all pixels here, then this would ensure that these two have same u and v, and these two have same u and v. Okay, so that's how you are doing this here. And
Mm.
Yes.
in practice, it is like a trade-off between these two terms. See, this is not at all looking into, pay your full attention here. This smoothness constraint is not at all paying attention to what are the intensity values of its neighboring pixels. And the earlier, this term, brightness constancy constraint, is not at all concerned about how much its neighbor has moved. What are the u and v resulting values? So these are looking at two complementary aspects. And how you do the minimization is, you have brightness constancy constraint plus lambda times the smoothness constancy constraint, and you try to minimize this equation and compute u and v such that you give some weight. So overall it has to be minimized. So there is a trade-off. For example, if you have to sacrifice too much of intensity variations are too much, okay, for the same movement, then what will happen? This term would shoot up because the intensity differences are quite high. So, well, if you make this, then lambda to be very high, you are giving more weight to say, I consider here 100, okay, for some normalization where I would consider it as 100. Then what would happen? It stops worrying about whether brightness are matching or not. It would simply be driven just to impose that my smoothness constraint is met. All pixels having same intensity is more important to me than having intensities. The contrary is I make lambda to 0, same as the earlier case, where it doesn't worry about what its neighbor is doing, what is his intensity values. It simply looks for its best match and settles down with that. And you take a trade-off between these two, and then you minimize that term. Okay, so E equal to Now you have minimization of EC, and you would empirically choose depending on the context. And choosing these weighting parameters is always a tricky stuff. So let's not venture into it at this point. For now, assume that you magically know what's the right lambda value. Okay, in practice, you could do some experiments and fix it, or you may be given it in some cases. Okay, so this is how you are imposing the constraint. Now, maybe I will leave you here on how you solve this equation. So this is good now. Okay. If it is a Horn and Schunk method, then it is something around that time it has come. This is proposed by Horn and Schunk, where they impose it throughout the image. And if you make this lambda value very high in this equation, it would essentially ensure that your whole image moves with has the same un value at every pixel. That's what Horn and Schunk method does. Okay, this is Horn and Schunk smoothness constancy constraint. That's what smoothness constraints. Not I hybridized both brightness constancy constraint with that was mistake. So it's Horn and Schunk smoothness constraint, which is a global constraint. And it does and the next one, which is referred to as locus and canade, it has come, if I'm not wrong, again 19, I should be having its reference 9, sorry, this one has come 1981, earlier one come even before that. Okay, now this is a nice stuff. This is again the homework for you to work it out and be there for tomorrow. But for now, you want to compute the displacement for a given pixel x comma y. You take, for example, a 5 by 5 patch around that. Earlier, you are imposing the smoothness constraint across all pixels here, but now you impose this constraint just around a 5 by 5 patch. Let's say I'm giving you some number, because when you simplify and try to get an interpretation, it becomes easier, and then we will again go back to a generalization. So for time being, you consider a 5 by 5 pixel, a 5 by 5 patch around the pixel. Now what I want you to do is, this is a different way of solving it now. Earlier, the way is different, where you are putting a global constraint, but now it's a local constraint, where if you want to compute u and v for a pixel which is there at the center of your patch, and now you assume that the whole patch moves with same displacement in x and y, is having same displacement in x and y. In other words, you write these equations earlier, brightness constancy constraint equation for each of those 25 pixels in that patch, then obviously that would be equal into ix for p1 plus iy time into u plus iy times of p1. Okay, hope this doesn't look like Greek and Latin for you now. This is just this equation I am telling you here, which we have been doing. Okay, that you now see here. Just to see the multiplication of the first row with first column and make interpretation here. For point p1, ix time for the point p1 multiplied with u plus for the point p1 iy multiplied with v should give you the I subscript t computed at p1. Okay, there are 25 points. For all of them, u and v are same. So how many unknowns are there now, and how many equations are there when we are considering 5 by 5 patch here?
25 equations and two unknowns.
Yes, we now reached the other extreme now. Okay, earlier we were having one equation, okay, at only just at point p1, two unknowns u and v. Now this seems better. You have more equations now, 25 equations. Okay, other end of the problem now, other extreme of problem you are getting now, and you just need to compute u and v. So how do you solve this equation? The clue is
We
also
can take
here.
any two equations.
No, that's don't want. We want to say that this you want to compute u and v in such a way that this equations are satisfied. Okay, so this, did you by any chance did we look at these kinds of issue earlier in our course? We did. and I want you to tell me where we exactly see similar problem, where you have more number of equations than, I should use word parameters, then it would ring in your mind quickly, than the parameters to be computed. Where did you see that?
in ransack.
Yes, before ransack we were discussing ransack, it is there, and linear least squares. We are now, the linear least squares has come to us in a slightly different form. It is still a linear least square problem here. How do you solve it now? Multiply both sides with A transpose,
A transpose. We'll take
right?
pseudo.
Right. Then take the inverse, and that should give you U and V. So this side, when you multiply with A transpose A, then multiply A transpose A inverse, you multiply both. What is the A transpose A size?
2 cross 2.
2 cross 2. Just take the inverse of it and multiply with both on both sides. It's equivalent to taking the inverse of a 2D matrix. That's all. So then you could get the U and V value. Okay, and this is what I'm just flashing you, the kind of equation you would be arriving at the end of the day when you do it. So this is what I want you to try before tomorrow's class, and come back and tell me what is the value of U and V. You do everything here considering the 5 by 5 patch here, you write the equations, you do compute what is the A transpose A, then you take the inverse of it, that you multiply A transpose A inverse with this, and then that should give you U comma V. When I take A transpose A, take a multiply it with the inverse of that on both sides. Okay, A transpose A, okay, A transpose A then this whole inverse I am taking. So you compute simply what is A transpose A first, then you will be getting a 2 by 2 matrix. Take the inverse of it. Okay, that's what you will be multiplying here, and then you finally compute what is your U and V, or at least don't worry about that, just put it in this format: A transpose A times U comma V, okay, equal to A transpose B. Please do the simplification. It gives you a very good understanding of dealing with this thing and a very good interpretation. And think if whatever you are arriving at has some similarities with something you had seen earlier, is that terms are similar to earlier one, and please put this hard work. Okay, and I'm sure it is worth, and it's very rewarding once you do it. Okay, I'll stop here, and see you tomorrow.